Vectors and resultants. The resultant vector is the combination of two or more other vectors. In other words, all we're doing here is adding two vectors or maybe three or four vectors and looking at one single vector that would represent the sum of those vectors, okay? In example 1, we're going to let u be a vertical vector pointing upward with a magnitude of 7 and v be a horizontal vector pointing to the right with a magnitude of 5. We're asked to find the resultant vector of u plus v, and when we do that, we're going to be figuring out the magnitude and the direction that goes with it, okay? Let's go ahead and start with the sketch. Vector u is a vertical vector pointing upward with a magnitude of 7. Okay, and at the end of that, because we're going to be adding on v, let's make sure I place this right. V is going to be a horizontal vector that is pointing to the right. Okay, so for the space that I have here, I can pretty much just go ahead and maximize the room that I've got there. Okay, so that is going to be vector u. It does have a length of 7. In fact, I should probably just take out the u. That's not going to really be necessary here. Go ahead and write that in as 7. Now, when I drew that, I didn't measure, say, 7 centimeters. Didn't do that. It's just 4 point something that's here. If you can draw them to scale, it's going to be easier to accept the result that you get from that diagram. Okay, in fact, you'd even be able to measure the length of the resultant vector, and that would represent the answer. Now, the way that I'm going to approach it is just do a general comparison of size here. So if that's 7, and vector v, which is going to get added onto this tip to tail, and that is horizontal to the right with a magnitude of 5, what I'll do is just make sure that it's a little bit less than that. Okay, so I have 4 and something, probably going out just a little bit past 3 is going to be all right. Okay, but I want to see that that vector is shorter than this one, but not also like substantially shorter. All right, now anything is done here with these two vectors, because we have a vertical and we have a horizontal, you do have the angle that sits between them. So we got a right angle there. The resultant vector is going to be the sum of these two vectors, which is going to take you from the beginning of u to the end of v. So that would be the resultant. Okay, and again, if you actually draw this to scale and you have all the right size angles in any of these problems, you could technically just measure that and you'd get an answer. Of course, when you do measure things, the values are going to be a little bit rounded off, so you can't treat that as an absolute answer. Okay, so what we're going to do is use other techniques that we know, like possibly Pythagorean Theorem, okay, and a little bit of trigonometry. In this case, because we have a right angle here, you can use Pythagorean Theorem to get the magnitude of the resultant vector. Okay, so I can take 7 squared plus 5 squared. That would be 49 plus 25, which is going to add up to be, let's see, 54, 74, I believe. You're going to get 74 out of that. Yeah, that would make sense. And then if you square root that, you're going to get the length of the magnitude. So you have different choices in how you can state that answer. Square root 74 is going to be exact answer. If we could do anything with reduced radical form, that might also look pretty good here. As far as the factors, I think, actually, I'm not really sure. I know it's even, so let me just test it out, because I'm really not that familiar with this number. Okay, so 74, if I divide it by 2, it's going to give me 37, which is a prime number. So we're not going to have any reduced radical form to go with that one. That is its own reduced radical form. Okay, so you could state the answer that way, or if you want, you can just go ahead and approximate, which would be all right in this case here. Okay, so it's about 8.6. Now, as an answer, that's pretty helpful in comparison to these, because you see that the hypotenuse would be the longest one. Okay, so it's approximately 8.6. All right, I might use that as my answer. All right, in addition to that though, so not just about the magnitude, not just how far out like this is, but the direction as well, the direction that this would be in. When it comes down to the direction, there are different ways that you can describe that direction. One of them that we're going to look at shortly is going to deal with navigation. And with navigation, you would have a north direction, and then measuring off of the north, you measure your degrees this direction, which is different than how we have seen these in just general pictures of angles. Okay, So there is an option that you can measure off of the north a certain degree amount, so that east would be like 90 degrees, south would be 180, then 270, and so on. There's other versions of how you can describe things using maybe north and east, because it's generally in that direction. I think for this one, just because we don't have any context to the problem, the way that I'll give the angle measurement is going to be off of the horizontal line. So if I imagine that I had a horizontal here. So again, from problem to problem, the way that you describe that angle, there's a little bit of an option. So for this one, I'm going to measure off of the horizontal. Okay, so to figure that out, to figure out how far I am off of the horizontal, what I'm going to do is figure out what this would be, figure out what that angle is. And that is a pretty easy thing to do if you've got a right triangle. Okay, for that, I can just simply use the arctangent. If I take the arctangent of the side opposite, which is the 5, and divide it by the side adjacent, the 7, that will give me this angle. All right, so I make sure my calculator's in degrees. Take the arctangent of 5 divided by 7. That gives us about 35.5 degrees. We'll call that 35.5. You can do that, and then the difference to the 90, so I'll just take a difference. That would be 54.5. Okay, so a way that you could state the answer, you could say that it has a magnitude, let's abbreviate, magnitude of 8.6, that's approximately 8.6. Direction would be 54.5 degrees off of the horizontal. Should spell that correctly. Off of the horizontal. Okay, so with the direction, there is a little bit more that needs to be included just to make sure that we know the way that we're measuring things here. Once we look at the navigation problems, it's going to be easier to make the determination that you should be given the angle measurements based off of north, south, east, and west. As mentioned above, if we're looking at a navigation problem, we're going to be measuring our angle or direction based off of a north line. With regards to direction, the course of a ship, plane, or other object, so that could even be something as simple as a person who is walking. The angle is measured clockwise from the north direction. Okay, so north, of course, in most diagrams is just pointing vertical. So our angle measurements, we're going to start at north, letting that be 0 degrees, and then moving this direction around is how we pick up degrees. Okay, so at east, that would be 90 degrees. At south, it'll be 180. West is 270. And then as you're getting close to that north, again, you're way up in the 300s, so 350. Once you get to 360, of course, you'd be right back at 0 degrees. All right, example 2. A ship proceeds on a course of 300 degrees for 2 hours at a speed of 10 knots, that would be nautical miles per hour. Then it changes course to 230 degrees, continuing at 10 knots for 3 hours. So same speed here, let me point that out. At that time, how far is the ship from its starting point? Okay, so what we want to do first is to kind of visualize or map out like what the ship is doing. By the way, they're giving you time and they're giving you speed. So the way that we're going to interpret that is a distance. And of course, at the end of the problem, it asks how far away it is. Okay, so if the ship is traveling for 2 hours at 10 knots, you can just multiply those values and say it's going to be 20 nautical miles away, right? 2 times 10 is 20 nautical miles. That's what you can get. So you want to remember that number 20. A little bit later on, same speed, 10, 3 hours is going to give you 30 nautical miles. So that'll be a longer distance that has been traveled. Okay, so let's try and visually map this out first. I'll start with a real simple compass over here. And this isn't my official diagram. This is just to get sort of a concept to like where this ship is going so that when I start to draw the picture, I actually have some room for it. All right, let's see. So it begins on a course of 300 degrees. All right, so this is 0 degrees, and we're going to be moving around in that direction, moving around clockwise. So 270 degrees is right there. So this is going to be 30 degrees up. I'm going to put a little 30 there. Okay, so I'm going to need to be able to draw a line that goes in that direction for 20 nautical miles. At the end of that line, when the ship changes courses, it heads in 230-degree direction. Okay, so a little compass for that one as well. 230 is going to be in this direction, which would be 40 degrees shy of the 270. Okay, so our ship is moving this way, then it's moving that way. All right, so when I build my diagram, it would be a good idea to start around here. I think that'll be a safe place to be. Okay, what I'm going to do is start with the compass. One of the great things about the compass is it's going to break everything into perpendiculars for this. Okay, and our first distance, which is going to be 30 degrees off of that line there. You don't need to measure exactly 30, but try and estimate it. Is also going to be, no, I got it mixed up here for a second, is going to be a distance of 20. Okay, so off 30 degrees from the west, you're going to go 20. And this, I might want to actually try and scale this. I think I can do this in inches. This will be fine. Got enough room. All right, so that'll be 20. Remember that was 2 times 10. Gives us that. Now, at the end of that line, or vector, right? At the end of that vector, we're going to change direction. So we're going to reset over here. Next, we're going to be 40 degrees south of the west line that we've got there. And that one, it's going to be closer to 45. So I'll draw it here. Okay, now that one is going to be a length of 30. This is 20 and that is 30. Okay, and because I had the space here and it worked out convenient, I went ahead and measured that at 2 inches, which means that this should be 3. So much further down there. Okay, and that's all going to help us see the answer and accept it a little bit better. All right, and that is the end. Ends up over here. And our question is to figure out this length here. All right, you were not asked to figure out the direction. Just not asked that part of the question. It just says how far are we from the very beginning. So that'll just be the distance. It is possible to figure out the direction, but we're only going to be looking at the distance for this problem. All right, there's a 30 here, right? We got that one. All right, and then we know things about angles. We do know things about angles. We just got to get them into the picture. Right here was 30 degrees to get to 300, right? That would be 30 over 270. Over here, 40 degrees, I'd mentioned that because at 230, you're 40 short of that. But maybe more importantly would be the measurement that's right here. So if that's 40, this is going to be 50. You get 50 degrees. So if I could figure out, just taking a big look at the picture here, if I could figure out the angle that's right here, I would have the total angle measurement there, and I'd have the 2 sides that are around it, and that would fit a law of cosines problem perfectly. I would have the included angle between 2 sides, which would allow me to solve for that. Okay, but how much is that angle? The trick to the question here is that when you draw the compass in each of those spots, the east-west lines, those run parallel to each other, okay? So when I draw this vector here, what I'm doing is creating a transversal that's passing through 2 parallel lines. Therefore, rules like corresponding angles, alternate interior, alternate exterior angles all apply. In this case, the 30 degrees here is going to be an alternate interior angle with the one that sits on the outside there. They're both going to be 30 degrees. So this is 60, right? Need to be complements. So we got 60, which means overall we've got 110 degrees. And now, using the law of cosines, we can set up, got to figure out where I got space to actually do this though. I'll try and squeeze it in here. We can set up this problem that, what we'll do is we'll call that little a there. We can say that little a squared is going to be equal to 30 squared plus 20 squared minus 2 times 30 times 20 cosine 110. And the great thing about this setup here, not that the law of cosines is ever really difficult to work with, but the great thing about this one is that all of your numbers are over here. So we're able to evaluate all of that at one time. All right, double check everything is here. We got the 30 squared, we got the 20 squared, we got the -2, we got the 30, we got the 20, we got the cosine 110, and I'm set for degrees. Gives me that answer, which is not going to be the length, I'll put the 0.4, I guess, which is not going to be the length of that. However, this represents a squared. So if I were to square root it, I get 41 point, let's call it 4. 41.4, these would be nautical miles. I'll just call them miles. That's fine. All right, and then when you take a look at the picture, probably sounds right. You got a 20, you got a 30. This is the biggest angle. That side should be the biggest side. Size-wise with these, yeah, 40 seems like it's a reasonable answer, and it is. That's how it's done. We're going to look at one more case where we can apply vectors to solve a problem. Forces on an object can be treated as vectors. By adding the vectors of each force together, tip to tail, the resultant vector can be found. This vector would be the resultant force. Okay, so as an example, if you had a bunch of people that are pushing or pulling on an object to make it move, each of those people would have their own vector representing their force. Okay, and if you take all their vectors and add them together, tip to tail, that's going to be the trick here. If you add them tip to tail, you'll be able to create one single resultant vector that tells us what is really happening to this object. Example 3, two forces act on an object. One of them is going to be 20 newtons, okay, that represents newtons, and it's a measurement of force. It's going to be 20 newtons pulling east, okay, let's draw a real quick sketch of that vector there. So 20 newtons, that's going to be heading east. And 10 newtons pulling in a compass direction of 150 degrees. Okay, so real quick sketch again. A compass, we would start at 0 degrees at the top. Any of these that refer to compass directions, we're going to have 0 up at the top. That is going to put 90 degrees over here, 180 there. 150 is going to be 30 degrees off of that south line, just for perspective. Okay, and that vector is going to have a magnitude of 10, so that one's going to be half the length of the one that we have there. Okay, and we only have two forces, but the way that we do this problem, you could have as many forces as you want being applied to this object. All right, let's suppose that our object is just a box, just so that we have something that we can draw here. Okay. All right, so let that be a box. This vector here, 20 newtons to the east, I'm going to go ahead and just draw it from the center of the object. And I think I can do these in inches too, just to scale it correctly. Might be able to get this guy to fit in here. Let's see if I can. Actually, I'm a little hesitant to go that far because I know the other vector is going to head down. So let's just do a single inch. That way I have enough space. Again, it doesn't actually need to be drawn to scale, but it does help. All right, so that will be 20 newtons. Go ahead and put a little n on that. From here, from the object, the other force is also being applied. Because remember, there's this object that's here, and maybe we've got ropes that are tied to it that we're using to pull it, or maybe we're standing behind it and we're pushing it in a certain direction. Okay, so in the beginning stages of this, that's little tiny compass right here. Might help out. All right, so we're going to be 30 degrees off of the south. And for my picture, it's only going to be ½ an inch. That's it. I'm doing a little picture here just to play it safe. That would be 10 newtons. Okay, so then if you had like a third or a fourth like force that would be in here, what you'd want to do is go from the center of that object and just keep pointing little vectors out in those directions. And you could have a case that people are pulling on a rope from different directions, and maybe you even have a vector that's heading in this direction or in that direction, which is counterproductive to the other two. Now these in general, they're working together. They're kind of guiding it into a certain area, and you can probably figure out that it's going to move that way, and it's going to move a little bit more to the east direction, a little bit more that way because that's a more powerful force that we have on there. Okay, but all the pictures for this type of a problem should start with your vectors all coming from your object. Once you have all of those, you're going to rearrange them. You're going to move them so that they're tip to tail. So I'm going to take that 10 Newton vector and just shift it over here. Okay, so it should run parallel. The length should be the same. All right, so I'll just move it to that spot, and then I don't really worry about that one anymore, right? So you can move vectors as you need them once you get to the point that you need to add them. So even if I had a third one that's pointing that direction, I would just add it to the end of that guy. It might not be a real convenient one if it's like pretty much in the opposite direction of it, but you might get the idea. Maybe I had one that's pointing here, I could just add it to the end at that one. And then all you do is you connect the beginning to the end. Now I should point out, because I'm thinking about how I was describing that, if you do have multiple vectors and they really start to get, like when you're trying to add them tip to tail, start to create a mess out of them, just add two vectors first. Add two vectors, figure out what the resultant is, and then add the next one onto the resultant. And have one new resultant from there. Okay, so this one only has two. It's a little bit easier to look at, but different ideas to consider if you have multiple. All right, you have a triangle. We have a triangle, and in fact, it's starting to look a lot like the last problem where maybe we can use the law of cosines again. If we can figure out the angle that's right here, we'd be in pretty good shape. Okay, so let's think about this. That is heading east right there, and if there was a compass, a little hesitant to draw it, but I'm gonna go ahead and put it right there. I made my picture so tiny. You've got 90 degrees from that west to south. You got 90 degrees there, and then it was already mentioned here with the 150 that it's 30 degrees off. So what you have is 90 plus 30. You have 90 plus 30, which means you've got 120 degrees right there. And now, yes, this is a law of cosines problem to figure out what the length of that is. Let's see, we'll go ahead and just put it over here. Again, it's gonna be a short problem. We'll go ahead and call that A again, just to make it look like the last one. Okay, so A squared is gonna equal 20 squared plus 10 squared minus 2 times 20 times 10 cosine 120. All right, and all that I can evaluate and then just square root. All right, so that equals 700 exactly, which is kind of interesting here. Reason is because the cosine of 120, if you use the reference angle that goes with it, which is 60, the cosine of 60 is 1/2. And that might explain why you didn't get this weird decimal number that's there. Anyhow, we're gonna square root it, which is gonna give us 26 points, so that's A equals 26.46 is what we get. All right, and what that is gonna represent this time is not a distance. In our last problem, it was a distance. For this, it's actually the strength here, which is gonna be newtons. Okay, so the way the object, when it's being pulled by 20 and 10, which together would add up to 30, would add up to 30 together, but since they're not moving in the same direction, you lose a little bit of that force, which is gonna drop down to actually 26.46. You can almost think that these two forces are slightly working against each other on there. Now, we're not actually done with the problem because it says, what is the resultant force? What is the resultant force? We have figured out what the strength is of it, but if we really want to talk about these as vectors, we need to apply a direction with this as well. So we're going to assume, unless it is told that we only want the amount of newtons or the amount of distance, that we should also figure out the direction that goes along with it. So let's figure out what that would be. We've got north up here, which is 0 degrees. We got 90 degrees there, so you know it's already 90. It's gonna go beyond 90 to get to that blue line I've got, okay, but it's not gonna go as far as 180. We do know that we've got 30 degrees here, yet we don't know how much is located right there, so you can't just subtract that from 90 and then complete this whole thing. However, we do have a picture of a triangle. I'll do a rough sketch over here now. We do have a picture of a triangle that has 120 degrees here. It's got a length of 20, a length of 10, and another length that we have discovered to be approximately 26.46. So we should be able to figure out this angle, the one that we're going to need to add on to 90. We should be able to figure out that angle using the law of sines. Okay, so the sine of 120, we're going to be able to match up with our new answer, 26.46, set that equal to the sine of, let's just call it x, over 10. All right, we're going to do some cross products here. We're going to do 10 times the sine of 120. Okay, that's this product here. We're going to divide that by this answer that we have, which I should be able to recall that last answer. So I'll just highlight it so it's a little bit more accurate than the 26.46. Okay, I'm going to divide by that number. Then this is going to represent the sine of x. So I need to arc sine that answer, and I get 19.1 degrees. Okay, x is going to be equal to 19.1 degrees. All right, so overall, let's go ahead and put our answer up here where I got some space. No, I'll put it down there, it should be fine. Overall, what we've got is 26.46 newtons at, make that look better, 26.46 newtons at not 19.1 degrees. We're going to need to add that on to 90 degrees, which is going to be 109.1 degrees. That is the resultant force, the force as far as newtons and the direction that it's actually being applied in.
Later, blah.